Number 7. Analyze and sketch the graph of r of x equal to x squared minus 2x minus 8 over x squared minus 2x minus 3 by determining the following. The first thing I want to do is go ahead and factor the numerator and denominator of this rational function. It'll make it a little bit easier for us to work with. So the numerator is going to factor into x minus 4 times x plus 2. And my denominator will factor into x minus 3 times x plus 1. So then we can go ahead and look at our domain. Well, this is a fraction. So if we remember, we cannot have 0 in the bottom of our fraction or in the denominator. So what we're going to do is take our denominator and set it not equal to 0. And it'll tell us what we're not allowed to have inside of our domain. So x minus 3 times x plus 1 cannot be equal to 0, or else our function will become undefined. Well, since I have two things being multiplied together, set equal to, or in this case, not equal to 0, I can use my zero factor property and say that x minus 3 cannot be equal to 0, and x plus 1 cannot be equal to 0. So then x cannot be equal to 3, and x cannot be equal to negative 1. Now, some of us may be able to go directly from this to our domain, and some of us may not. So I'm going to go ahead and assume that we can't, and we're going to use a number line to help us find our domain. So what we're going to do is we're going to put the points that we cannot have on here, and I'm going to put an open circle around those points. So remember, I cannot have these numbers. And if we remember, when we're finding the domain of a function, we start with all real numbers. So every number, and then we just take bits and pieces of it out. So that means that the rest of this line will be my domain. So our domain will be intervals for each piece of the number line that I have shaded in. So my domain will be negative infinity to negative 1, and we're going to use a parenthesis because we're not allowed to have negative 1, union negative 1 to 3, and then union 3 to infinity. Then after this step, we would simplify our function if we can. So I would look to see if I have any common factors in the numerator and denominator of my rational function. I don't. So I'm going to go ahead and move on to our next step. And that's going to be finding any asymptotes of our equation. Usually we start out with our vertical asymptotes first. So what I'm going to do is, after I reduce my fraction or cancel out any of those common terms, I'm going to take the denominator of my fraction and set that equal to 0. And then whatever x is equal to will be our vertical asymptotes. So I get x minus 3 equals to 0, and x plus 1 equals to 0, using my zero factor property. And then x equals to 3, and x equals to negative 1. Then we can use the multiplicities of these vertical asymptotes to tell what's going on around this asymptote, which is really nice. So looking back at my original function, or our reduced function, the multiplicity of x equals to 3 is going to be 1, because I don't have any power for that factor, which tells me it's a power of 1. And we're going to do the same thing for negative 1. It also has a multiplicity of 1. So if we remember, the multiplicity on our vertical asymptotes will tell us whether or not we're going in the same direction on either side of the asymptote or opposite directions. Well, since it's an odd multiplicity, one side will go to infinity and one side will go negative infinity. And same thing for this asymptote. And to kind of give you a visual, so let's say that this dotted line here is my asymptote. So one side, my function will shoot up to positive infinity, and the other side, my function will shoot down to negative infinity. Or it could be the reverse. So the left-hand side shoots up and the right-hand side shoots down. If we had an even multiplicity, they would be going the same direction around this asymptote. So both sides up, or it could be both sides down. But this is really useful whenever we're graphing these. All right, so then we can look at our horizontal or oblique asymptotes. Now, if you remember, we're going to use the degree of our numerator and the degree of our denominator to find out what those asymptote is going to be. So let's go back to our reduced rational function, which is the original one. The numerator has a degree of 2, and my denominator has a degree of 2. So remember for the exam that you're going to need to know what the different degree combinations will cause to happen. So if the numerator and denominator have the same degree, then we're going to have a horizontal asymptote of y equals to the ratio of our leading coefficients. So we're going to make a fraction out of our leading coefficients. So since we have the original function in just factored form over here, I'm going to go back to the original. So the leading coefficient for my numerator is going to be 1, and the leading coefficient for our denominator will also be 1. So our asymptote will be 1 divided by 1, or y equals to 1. Now don't forget, we do need to check to see if our function will ever cross this horizontal asymptote. So what we're going to do is we're going to take our function and we're going to set it equal to that asymptote. And if we get x equals to a real number, we know it crosses at that point. If we get some kind of imaginary number or something that's impossible, we know it will not cross. So what I'm going to do is multiply both sides of my function by x minus 3 times x minus 1. So it's going to give me x minus 4 times x plus 2 equal to x minus 3 times x minus 1. And then we're going to multiply both sides out, which of course we can just use our original function to do so. So it's going to be x squared minus 2x minus 8 equals to x squared minus 2x minus 3. Now I want to move all the x's to one side. So I'm going to subtract x squared from both sides. And then subtract or add 2x from both sides. So we get negative 8 equals to negative 3. Well, that's not possible. So our function does not cross our asymptote. Then it wants us to find any intercepts if they exist. So for our x-intercepts, now we could go about this by setting the entire function that we have here equal to 0, and then solving for x that way. Or we could kind of take a little bit of a shortcut. I can just take the numerator of my rational function, so x minus 4 times x plus 2, and set that equal to 0. It'll give us the exact same answers, which is nice. And again, since we have two things being multiplied together, set equal to 0, we can use our zero factor property. X minus 4 equals to 0, and x minus 2, or plus 2, equals to 0. So x equals to 4, and x equals to negative 2. And then we can use our multiplicities for these to tell whether or not our function will be crossing or touching the x-axis, which is really nice. So for x equals to 4, my multiplicity is 1. So again, we're going to look at the power on that factor. So an odd multiplicity for an intercept tells us we're going to be crossing the x-axis. And then for x equals to negative 2, we also have a multiplicity 1. So again, we're going to be crossing the x-axis. Now let's get our y-intercept. So we're going to find it the good old-fashioned way. So I'm going to set my x is equal to 0, solve for y. So 0 minus 4 times 0 plus 2 over 0 minus 3 times 0 plus 1. What's going to give me negative 4 times 2 over negative 3 times 1, which will be negative 8 over negative 3. So y equals to 8/3. And then one extra step that's not actually listed on here is creating a number line using all of our vertical asymptotes and any undefined points and our x-intercepts to see where our function is positive and negative, because that'll really help us when we're graphing this function. So I'm going to go ahead and put my x-intercepts on there. So negative 2 and positive 4. And then we're going to put our vertical asymptotes of negative 1 and positive 3. And we're going to find out whether or not our function's positive or negative in each of these intervals that we've created. So what I need is to test a number that is less. So what I need to do is test a number that is less than negative 2. So I'm going to test negative 3. So I'm just going to plug that into my function and get the answer. And it's 0.58. So it's a positive number. I'm going to put a plus. Then I'm going to need a number between negative 2 and negative 1. So I'm going to test negative 1.5. Which gives me negative 1.22. So it's negative. Then a number between 0 negative 1 and 3. I'm going to go ahead and use 0, since we already calculated that. And that was 8/3. So positive. Then a number between 3 and 4. Let's go ahead and use 3.5. That gives me negative 1.22. And then a number greater than 4. I'm going to go ahead and use 5, which gives me 0.58. So then we can tell what's going on with our function around these asymptotes and around our intercepts. So we said at negative 2, we're going to be crossing the x-axis. So since I go from positive on the left of negative 2 to negative on the right of negative 2, I must come from above, cross, and then go below. And then at positive 4, we're also crossing the x-axis. Well, again, this time we're negative on the left and positive on the right. So I'm coming from below and going above, which is really nice to know. Then at negative 1, we have our asymptote, our vertical asymptote. And at positive 3. Well, a negative on the left-hand side of negative 1 means that I have to get really close to that asymptote and then shoot down. Well, we know we have to go opposite infinities around this asymptote, which makes sense because I'm positive up here above, which means I must shoot up. Similarly with 3. I'm positive on the left-hand side of 3, so I have to be shooting up when I get close to that asymptote. And I'm negative on the right-hand side, which fits with the multiplicity, so I shoot down. But let's actually do this on the graph. So the first thing I'm going to do is graph all of my intercepts. I have positive 4 for my x-intercept and negative 2 for an x-intercept. I also have a y-intercept of 8/3, which is right about 2.67. And I'm going to plot any asymptotes I have. So I have a vertical asymptote at negative 1. And a vertical asymptote at positive 3. And then we also have our horizontal asymptote at y equals to positive 1. Alright, so now that we have all of our intercepts graphed and we have our asymptotes graphed, we can go ahead and start graphing our function. Now we said over here at x equals to negative 2, we're going to be coming from below and going above. And we know that we're not going to be crossing that horizontal asymptote. So we're going to get really close to it, but never actually touch it. And then on the right-hand side of negative 2, we're already heading down. We have to stay negative. And we can't cross a vertical asymptote ever. So we know for sure that it's going to look something like that. Then at x equals to 4, we're going from below to above. So on the left-hand side, I have to stay negative, and we can't cross that vertical asymptote, so it's going to shoot down to negative infinity. On the right-hand side of 4, I have to stay positive, but we're not going to be crossing that horizontal asymptote, so it's just going to get really close to it. Then the in-between parts. So we said that on the right-hand side of negative 1, we're shooting off to positive infinity. And on the left-hand side of positive 3, we're shooting off to positive infinity. And we know that we have to cross our y-axis, so we're just going to connect those lines. And if we wanted to, we could plot some points in between negative 1 and 3 to get a more exact graph. But we're just looking for a sketch, so something that's roughly correct and gives us all the major details of our graph. So that's going to be it.